Hello and welcome to Chemistry with Dr. Clark. In this video, I'd like to talk about reaction quotients. This is part 2 of a 2-part video series. In part 1, I talked about the theory behind reaction quotients, how you calculate the Q, and how you compare it to the value of K. In this part of the video series, what I want to do is some actual calculations. So if you haven't seen the first part of the video, you should probably pause here and go back and take a look. Okay, the most pertinent thing from the first part of the video was the comparison of KSPs versus QSPs. Solubility product constants versus reaction quotients. Okay, so the solubility product constant is the KSP, the reaction quotient is the QSP. What we're going to do is we're going to give you the KSP, we're going to ask you to calculate the QSP, and then we're going to compare. So, if you calculated the Q, and your Q is much smaller than your K, what that means is then when you have mixed two chemicals together, the amount of material dissolved in the water is so low that you haven't met the threshold, right? Like, you could actually dissolve more if you wanted to. So you've poured in a cation, you've poured in an anion, and you have not reached the maximum amount, and therefore no precipitate forms. Okay, you can actually dissolve more of the solid. Now, if you take your two chemicals and you mix them together, and you have too much, okay, you have more dissolved than really should be dissolved, what'll happen is your Q will end up being bigger than your K. And if you have too much of this stuff dissolved, then it's going to stop being dissolved. And if it stops being dissolved, it turns back into a solid, and the solid will settle to the bottom of the container. So a precipitate will form. Now, if you're really, really lucky, you could add exactly the right amount, okay? There's a certain amount of the cation and anion that can dissolve, and if you were lucky enough to add exactly the right amount of cation and the exact amount of the anion, then your K and your Q will be equal. Now, that's not going to happen. That is extremely rare, right? It would be kind of like winning the lottery. But if you happen to do that, what you have is you've created a system that is at equilibrium. You have dissolved the maximum amount. You have a saturated solution. Okay, that's quite rare. So for these problems here, really, you're going to talk about the first or the third possibility. Is your Q too small or is your Q too big? If your Q is too small, you don't get a precipitate. If your Q is too big, then you do get a precipitate. And the way that you can tell that a problem is a reaction quotient problem is that the question will revolve around predicting precipitates forming. So it could say, please predict whether a precipitate forms. Or it could say, will a precipitate form? Okay, it's all about, is there a precipitate going to occur? Okay, that's how you can tell you have this type of problem. Now, it's my suggestion that you memorize this little table here. Memorize what happens when the Q is too small. Memorize what happens when the Q is too big. It will make these problems go a lot easier for you. All right, so let's say that we're going to take a look at an actual problem. So in this problem it says, will a precipitate of barium sulfate form? Now the minute it starts asking, will a precipitate form, you know that this is a reaction quotient problem. Okay? So now they give us some information. They tell us the amount of barium nitrate, they tell us the amount of sodium sulfate, and they give us the volume of water. They also give us the value of KSP so that in the end, after I've calculated my Q, I can compare it to my K. Okay, so I've got something to compare to. Now, these problems here are very, very similar to solubility product constant problems, KSP problems. If you're fairly familiar with those, these are like the extension to those. They build on top of them. If you're finding that the KSP might be a little bit shaky, you're not totally sure of it, or as you go through these problems, you find that they're moving quite quickly, I do have a series of videos that talk about KSPs. It might be worth stopping here and going back and taking a look at them. Again, I've put those links in the description below. So if we're going to do a problem on reaction quotient, the very first thing we need to do is decide which chemical is the one that really doesn't like water, that really doesn't like to dissolve, and we need to write an equilibrium for it. Now in this problem, you're given 3 chemicals: barium sulfates, barium nitrates, and sodium sulfates. How do you know which one is the important chemical? How do you know which one is the one that doesn't like to dissolve? That it'll sit at the bottom of the container as a lump of solid and only very rarely break up to give you ions. The chemical that has the KSP is the important one. So in this problem, barium sulfate is going to be the focus of my problem. So the first thing I need to do is talk about barium sulfate solid dissociating in water. So let's write that equilibrium. So I've got barium sulfate solid. It's going to be in equilibrium with its ions. So if it's barium sulfate, the first ion is barium, and the second ion is sulfate. Now, when you do this, there's a number of things that you have to include. The first one is the charges, okay? While the barium and sulfate are together, they have charges, but by being together, the charges cancel. So if you got a positive and a negative, right, they cancel themselves out. The minute, though, that it dissociates, breaks up, well, then they're separate and they're free, and you have to show what charge is on it. So if you look up barium on your periodic table, barium is in table or column number 2, which means it has a 2+ charge. If you look up your sulfate on the polyatomic ions table, okay, it has a charge of 2-. And once they break up into ions, they are now aqueous. That's how they become aqueous. They go from the solid to split up into ions, and the ions are surrounded by water. So this will be aqueous. This will also be aqueous. And finally, you have to make sure it's balanced. In this particular problem, 1 barium gives me 1 barium. 1 sulfate gives me 1 sulfate. So this thing is balanced. For every one of these, you get 1 barium and 1 sulfate. This is my equilibrium. Okay, so if you want to label it, we can. This is my equilibrium. It'll always involve the chemical that you are given the KSP for. It'll always be the solid breaking up into its ions. Now I need to write the equivalent of an equilibrium expression. Okay, if I actually knew the concentration of the barium and the sulfate at equilibrium, then I would write an equilibrium expression and I'd use the KSP. But for this particular problem, when I tell you the amount of barium nitrate and the amount of sodium sulfate, they're not equilibrium amounts. They're initial amounts. So you can't talk about a KSP, but you can talk about a QSP, a reaction quotient. This is my reaction quotient. Okay. Now a reaction quotient and an equilibrium constant basically set up the same way. Okay, this is going to be equal to products divided by reactants. So if we go through and pick out our products, my first product is a barium 2+. This problem is all about concentrations, so I'll put square brackets to show concentration. And the number that was used to balance the equation for barium becomes the power for barium. So it's barium 2+ to the power of 1, because there's a 1 used to balance the barium. Now I have a second product. So my second product is SO42-. Again, I want to talk about its concentration, so square brackets. And the number that I use to balance it is a 1, so this is power of 1. Under normal circumstances, products go in the numerator and the reactants would go in the denominator. So normally the barium sulfate would be down here in the denominator, but the barium sulfate is a solid and solids are not included in equilibrium expressions or reaction quotients. Okay, they follow the same set of rules. So because this is a solid, I'm going to leave it out and I don't have a denominator. Okay, this is my reaction quotient. If this here had been a K, KSP, then this equation would be perfectly correct. But if this was a K, then these two concentrations have to be equilibrium concentrations, right? If you have an equilibrium constant, you have to have equilibrium concentrations, which you don't. You have initial concentrations. So because you have initial concentrations, that's why we're using the Q rather than the K. Now, if I know the value of this concentration and I know the value of this one, I'll multiply them together, find the value of Q, and then compare it to the K. Okay, so for this problem, all I need to know is how much barium 2 plus do I have and how much sulfate 2 minus. So let's talk about the sources. Okay, I've already talked about the barium sulfate, so that's done. Now the problem tells me you have 2.5 times 10 to the minus 5 moles of barium nitrate. The barium nitrate is going to be my source of barium. That's where the barium comes from. Now I did give you a moles, and I also told you the volume of water it was dissolved in. Okay, so let's draw ourselves a little picture. Imagine it like a beaker, glass, some sort of container. It has this much water in it. There's my water. And I've dissolved into that barium nitrate. There we go. Now what you're going to notice with these problems is that one of the chemicals is something that you need. See, I needed the barium, so I have barium. But in this container, I really want the barium to dissolve, right? When I put the barium in this container of water, I want it to dissolve really well. And in order to dissolve really well, it needs a partner that dissolves really well. And of all the chemicals that can be a partner with barium, nitrate loves water one of the most, right? Nitrate loves water. If you've got something nitrate, it's guaranteed to dissolve in water. So if you want to make sure this barium dissolves, you need to put it with a partner that loves water. So in these problems, you're going to often see something nitrate, because nitrate is an easy way to get our chemical to dissolve. Now, this here is all about concentration, and I did not give you the concentration. So the first thing we're going to have to do is calculate concentration. Concentration is moles divided by volume. So concentration would be the number of moles, 2.5 times 10 to the minus 5 moles, divided by the volume of water that you've dissolved in, 3.25 liters. So if we haul out our calculator, 2.5 times 10 to the power of minus 5 divided by 3.25 gives me 7.7 times 10 to the minus 6 moles per liter. This is the concentration of the barium nitrate. Now, because this stuff dissolves, okay, and what does dissolving mean? Dissolving means taking your compound and splitting it into ions. So the minute the barium nitrate hits the water, it's going to split up. So I don't need the concentration of the original chemical. What I need is the concentration of the barium nitrate after they've split up. Because when this splits up, it's going to split up to give me some barium 2 pluses, and it's going to split up to give me some nitrate 1 minuses. Now when it splits up, this has 1 barium, so this is 1 barium, but it has 2 nitrates, so it'll give me 2 nitrates. Now, even though it's split up to give me barium and nitrate, is the nitrate important? Do you see the nitrate over here in my main equation? No. So the nitrate, even though I have some, is not really important. It's like it's sitting there in the beaker just kind of watching what's happening, but it's not actually getting involved, right? This would be a spectator ion. It's just watching. The barium is the important piece. So now let's talk about the splitting up. If you had 1 barium nitrate, you get 1 barium 2 plus. If you had 2 of these, let's say I split up 2 of them, I would get 2 bariums. If I had 5 of them, I'd get 5 bariums, right? It's a 1-to-1 relationship. However many barium nitrates you have the same number of bariums. So if you started with 7.7 times 10 to the minus 6 of these, then you're going to end with 7.7 times 10 to the minus 6 moles per liter of the barium 2 plus, right? Because this is a 1-to-1 relationship. So you now know the amount of barium. So if I'm going to calculate my Q, QSP equals, how much barium 2 plus do you have? I have 7.7 times 10 to the minus 6 to the power of 1. Now, this is not the concentration at equilibrium. This is the concentration at the beginning, because this is going to get poured in and mixed with the sulfate and make barium sulfate. Okay, so this would be initial amount. All right, so you know where we're going with this. You just did the calculation for barium nitrate. Now we have to do the calculation for the last chemical. So again, let's talk about a beaker. Here's my beaker. Here's the water in the beaker. So we've talked about barium sulfate. It was our most important chemical. It's the one we set up the Q for. Then we talked about the barium nitrate, so it's done. The only chemical I have left is this many moles of sodium nitrate. And again, it's in the same amount of water. So in this second beaker, I've got sodium sulfate. Okay, so I'll move it up in a second. Now again, I have given you the number of moles, I have given you the liters, but this equation is all about concentration. So the first thing I'm going to have to do is calculate concentration, moles over volume. So the number of moles is 1.8 times 10 to the minus 4. And the volume of water is the same because I'm putting it into the same container. So 3.25 liters. Okay, so let's see if we can move this up and give ourselves some room for calculations. So my concentration is going to be, let's pull out our calculator, 1.8 exponent 4 minus divided by 3.25 gives me 5.5 times 10 to the minus 5 moles per liter. And again, just like before, this is the concentration of the chemical together. But this chemical here loves water. The minute you put it in water, it's going to split up. How do I know it loves water? Because it has sodium, right? I really need to know what's happening with sulfate. So sulfate's the important piece. So if sulfate's the important piece, it just needs a partner that will help it dissolve in water. So if you're going to choose a partner that helps you dissolve in water, sodium is an excellent partner. If you have a sodium something, they all love water. So if you want to guarantee that this sulfate is going to dissolve in water, if you put it with sodium, you're putting it with a partner that loves water. Okay, so you're going to see a lot of sodiums and a lot of nitrates mixed up with the chemicals that we're actually interested in. Okay, so again, let's talk about this splitting up. Because in water, it does split. So you have sodiums, so sodium 1 plus. And this thing has 2 of them, so there's going to be 2 sodium plus. It's going to break up and give you sulfate, so SO42 minus. So even though it has 2 sodiums, it only has 1 sulfate. Okay, so 2 to 1. Just like the last time, one chemical has a 2 in front of it, the other chemical has 1. And just like the last time, the chemical with the 2 in front of it is not the important chemical, right? If we think back to our original reaction quotient, what chemical am I interested in? I'm interested in the sulfate, not the sodium. So when I take a look at this, right, it's the sulfate that I'm interested in. And it's a 1-to-1 relationship. For every 1 sodium sulfate, you get 1 sulfate. So if I have this many sodium sulfates, then I have this many sulfates. 5.5 times 10 to the minus 5 moles per liter. Now, let's say you did want to know how many sodiums you have. Because it's a 1 to 2, right? For every 1 of these, you get 2 of these. Your concentration here would actually be double. So 2 times 5.5 times 10 to the minus 5. Right? Because you're getting 2 of them. You're getting twice as many, so you'd have twice this number. Now, in this case, the sodium is not what I'm interested in, and therefore I can just ignore it. All right, so I now have the amount of sulfate. So if we put that into our calculation, how much sulfate do you have? I have 5.5 times 10 to the minus 5 to the power of 1. And really, the hardest part of this problem is calculating how much of the chemicals you have initially. How much of the cation, how much of the anion. Because once you have those 2 numbers, it's just put them in, use your calculator, and find your Q. Right? This part of it is quite straightforward. So we take our two numbers and multiply them. 7.7 times 10 to the power of minus 6. Now, it's to the power of 1, but power of 1 doesn't change anything. Times 5.5 times 10 to the power of minus 5. Again, power of minus 1. If you put anything to the power of 1, it doesn't change it. So that would give me a Q that is 4.2 times 10 to the power of minus 10. Right? If I mix these two chemicals together, this is the Q I get. Now you have to do your comparison. You're going to do QSP versus KSP. Your QSP is 4.2 times 10 to the minus 10. Your KSP, right, I've kind of got it moved off to the top there, but if we bring it down, remember it was 1.1 times 10 to the minus 10. So 1.1 times 10 to the minus 10. Okay, so let me move it back up so we can see our calculations again. Right about there. Perfect. Now you're doing a comparison. 4.2 times 10 to the minus 10 versus 1.1 times 10 to the minus 10. Now they're both 10 to the minus 10, but this one's a 4 and that one's a 1. The Q is bigger. So if the Q is bigger, that means these two concentrations were too big, right? Because this is the K you should get, but your Q is too big. You got too much. So how do you get a Q that's too big? Your two concentrations are too big. So when you take these two containers and you mix them, you're mixing together too much barium and too much sulfate. Too much of it is dissolved. So if you have too much dissolved, what is the extra going to do? Group up, fall to the bottom as a precipitate. Okay, and if you think back to the very first page, it says right here, if your Q is bigger than your K, you will get a precipitate. So because my Q is bigger than my K, I will say a precipitate forms. Now, if whoever's giving you these problems allows abbreviations, precipitate is too big a word for us to write out over and over and over and over. So we like to abbreviate it as a PPT. Okay? If you're allowed to do that, that's excellent. If you're not, you're kind of stuck writing out precipitate. Okay? And that is a QSP problem. Now let's say we want to try one more. This one here is a little bit harder because instead of giving you moles and liters, I've decided to give you grams and milliliters. Okay, so there's going to be some extra steps here. But again, you can see it says, will a precipitate form? The minute you see will a precipitate form, you know you have a reaction quotient problem. Okay, it's like the warning sign. It's like a little flashing light that says reaction quotient, warning, right? It tells you which one to use. Okay, so in this problem, it talks about calcium carbonate, talks about sodium carbonate, Cr sodium, and it talks about calcium nitrate, Cr nitrate, right? You want to dissolve calcium, put it with something that loves to dissolve, nitrate. You want to dissolve carbonate, put it with something that loves to dissolve, sodium. And you can see that I've given you a KSP. Now in this problem, the most important chemical is the one that has the KSP. It's the one that gets the equilibrium. So let's rewrite our calcium carbonate. So CaCO3, solid, in equilibrium with its ions as they break up and dissociate. So calcium carbonate is made up of calciums and carbonates. You have to put in the charges, right? Calcium is in column number 2, so it's a 2+. Carbonate is a polyatomic ion. It has a charge of 2-. The minute that they break up, they become aqueous. So aqueous and aqueous. And you got to balance this. For every 1 calcium carbonate, you get 1 calcium and 1 carbonate. So it is a 1 to 1 to 1. Now I'm going to write my reaction quotient. QSP equals products on the top, reactants on the bottom. First product is a calcium 2+, square brackets to show concentration. You use the 1 to balance it, so it's a power of 1. If it was a power of 2 when you did your calculation, it would just mean you'd have to square it, right? It's just a power. The second product is the CO3 2-, square brackets to show concentration. You use the 1 to balance, so the power is 1. In the denominator should be your reactant, but your reactant is a solid, so you get to leave it out. Okay, your Q's will never have a denominator, ever. So if I knew my two concentrations, I could calculate my Q and my problem would be done. So let's talk about where am I going to get the calcium and where am I going to get the carbonate. Okay, so we've already dealt with the calcium carbonate. So what's the next chemical that we talk about? Sodium carbonate. Okay, so let's talk about my container here. It has sodium carbonate. Now for my sodium carbonate, I'm telling you a mass. That's a lot harder than a moles, right? In the last problem, I would have told you the moles of sodium carbonate, but in this one, I'm giving you a mass. I'm also telling you how much water you're putting it in, 425 milliliters. Okay, in the last one, I gave it to you in liters, and we like liters. Liters are good. So we have to do a couple of things. First off, we need to change milliliters into liters. In order to change milliliters into liters, you divide by 1,000. So this would be 0.425 liters, right? Just divide it by 1,000. Now, if you have a mass and you want to convert it into moles, we have a little formula for that. The number of moles equals the mass divided by the molar mass. Okay, so if I want the number of moles, N, I need to know the mass. That would be 0.025 grams. And the molar mass comes from your periodic table. Basically, you go to your periodic table, you look up how much each of these atoms weigh, and you put it all together. Okay, so if you have 2 sodiums, each sodium weighs 22.99, right? You look it up on your periodic table. You got 2 of them, so it's times 2. Plus, you've got 1 carbon. A carbon weighs 12.01. Plus, you've got oxygen, which weighs 16, but you got 3 of them, so times 3. So the molar mass of this would be 105.99 grams per mole. So my number of moles would be 0.025 divided by 105.99. That gives me 2.4 times 10 to the minus 4. Now grams and grams cancel out, so that leaves me with just moles. See, I had to do extra work here to find the moles, and in the last problem, I just gave you the moles. Okay, and sometimes that happens, right? Sometimes in these problems, they'll just tell you the moles, so you'll know it, but sometimes they'll make you work for it. And that's what I've done here. Now, once you know the number of moles, just like in the last problem, I can calculate concentration. So concentration is moles over volume. So you now know the number of moles. 2.4 times 10 to the minus 4 moles. And the volume should be in liters. And we already changed it into liters. So this is 0.425 liters. So my concentration is 2.4. I'm just going to leave the number in my calculator. Divided by 0.425. Gives me 5.5 times 10 to the minus 4 moles per liter. Now in this type of problem, in the will they precipitate form kind of problem, this is probably as hard as it's going to get. Okay, the hardest I can do is to give you the chemical as a mass, because then you have to find the number of moles and then you have to find the concentration, right? You had to do a lot of work to get the concentration. Okay, that's probably the hardest thing that I can do in this problem. Now, like the last one, this concentration is for the chemicals together. But I don't want the concentration of the chemicals together. I want their concentrations separate. So when this gets put in water, it is going to split up. What is it going to split up to give me? Sodiums, so sodium 1 plus, and there's 2 of them, so 2 of those. And carbonates, CO3 2 minus. And there's only 1 of those, right? 1 carbonate. Now, between the sodiums and the carbonate, which one do I need? I just need the carbonate. So this sodium, even though it's there, is not important to me, and I'm going to ignore it. Now, I love this problem. right? For every 1 sodium carbonate, you get 1 carbonate. It's 1 to 1. So whatever concentration of sodium carbonate you have, that's the same as the concentration of the carbonate. So the concentration of the sodium carbonate was this. So the concentration of the carbonate is 5.5 times 10 to the minus 4 moles per liter. Okay, well, let's put that in my calculation. How much carbonate do you have? 5.5 times 10 to the minus 4 to the power of 1. I still need to know how much calcium 2 plus is there, right? I haven't found that yet. All right. Now, if we go looking at the second chemical, it says that you're adding this to a solution of calcium nitrate that has a concentration of. Now, you should be like, hold on. You made me work so hard for the first one, right? I had to turn a mass into a moles and a moles into a concentration, and you're just going to give me the other concentration? Okay, in these problems, a lot of times, if they make one of the chemicals really difficult, they will make the other one really easy. So for this second chemical here, basically they're saying, oh, here's your container. It has calcium nitrate in it. So calcium nitrate. And somebody already did all the calculations for you, and they're telling you that the amount of calcium 2 plus is 7.5 times 10 to the minus 5 moles per liter. Right? Somebody has already done all of this for you, and they've already popped out the answer at the bottom. And that often happens. One chemical will be really hard, and the other one is just like given to you. So this concentration would be 7.5 times 10 to the minus 5 to the power of 1. Right? One easy, one hard. But the problem is saying, if you took this chemical and you took this one and you mix them together, will you get a precipitate or not? Do you have too much of these chemicals or too little? If you have too little, they'll just stay dissolved and nothing happens. If you have too much, when they mix together, they form a solid that falls to the bottom of the container. Okay, so if we haul out our calculator and do the calculation. All right, I've got 7.5 times 10 to the power of minus 5 to the power of 1, which doesn't change it, times 5.5 times 10 to the power of minus 4, again, to the power of 1, which doesn't change it. And that gives me 4.1 times 10 to the minus 8. All right, excellent. Now this is your compare and contrast, right? You're going to do QSP versus KSP. Your QSP is 4.1 times 10 to the minus 8. Your KSP is 4.7 times 10 to the minus 9. Now, when you're talking about these numbers here, whichever one has the bigger negative number. See, this is 10 to the minus 8, this is 10 to the minus 9. Whichever one has the bigger negative number is the smaller one, right? 10 to the minus 8 is bigger than 10 to the minus 9. Okay, when you're coming to the powers, the one that is like the more negative, 10 to the minus 9, that actually gives you the smaller number. So in this case, your Q is bigger than your K. That's telling you that you got too much calcium 2 plus, you got too much carbonate, and if you got too much, it's going to precipitate. So a precipitate forms. And that's how you do a reaction quotient problem, right? You figure out how much of each ion you have, throw it into your Q expression, and then do your comparison. If the Q is too small, nothing happens. No precipitate, no anything. If your Q is too big, then you get a precipitate. And that's when you get the nice cloudy white solid form and it'll settle to the bottom, or a nice cloudy yellow solid and it'll settle to the bottom. All right, and once again, I'd like to say thank you for joining me here at Chemistry with Dr. Clark.